All right, now we're getting to everybody's favorite part of any unit, applications. This is where it gets really fun. So we want to understand how to find and use component forces in applications of vectors to find other information about vectors, really. These are some applications of vectors: displacement, velocity, acceleration, and force. Usually force is in newtons, but force can also be in pounds. Remember, if you have, well, I guess not necessarily remember, if you have taken physics, you would know this. If you haven't, that's okay. But we also have force can be in pounds, where pounds can be a mass or it can be a force. That's a little confusing, I know. Anyway, I digress. Let's move on. So I'm going to go through this a little bit quick because this should hopefully make sense for these first couple examples. So when we have two vectors that are going in the exact same direction in an application problem, or even not, but in this case, so if I have a plane that is flying at 100 kilometers an hour. And remember, here we have the plane is traveling with a velocity relative to the ground, which is the vector sum of the plane's velocity relative to the air plus the wind velocity. So that's what we would call the resultant velocity. How do we get that? Well, I have the plane is moving in some direction at 100 kilometers an hour. The wind is blowing in the same exact direction at 25 kilometers an hour. So together, we can add those two, and we end up with the resultant velocity is 125 kilometers per hour. That should hopefully make sense. What if the two things are going in exact opposite directions? Same thing, I can add the plane's velocity, it's going at 100 miles an hour, and I can add a negative velocity for the wind, or I can subtract the velocity. Remember that those are doing the same thing, so whether you add a negative number or just subtract two numbers, it's the same thing mathematically. So in this case, the resultant velocity of the airplane would be 75 kilometers an hour. The only thing to keep in mind is make sure that you have the same units when this scenario is occurring. Moving on, what if they are not going in the exact same direction? So if I have a plane flying at 100 kilometers an hour, and let's say that this is south, just for argument's sake, and the wind is blowing west at 25 kilometers an hour, what is the actual speed of the plane, or the resultant velocity of the plane? Well, these are all vectors, where the magnitude of the vector in this case is representing the speed. All right, so this is where we have to understand that, when there's application and we use the word magnitude, that is going to be the units of whatever the context of the problem is. So in this case, the magnitude is kilometers an hour for both of these two vectors. Now, because these vectors are at right angles to each other, these are the components that make up the resultant vector. So if I know the two legs of a right triangle, it's very easy for me to find the hypotenuse of the right triangle. So in this case, if I call this b sub y and this one b sub x, where this is b sub x and b sub y, I know 100 squared plus 25 squared equals r squared, and this leads me to my r value of 103.1 kilometers an hour. So I can just use the Pythagorean theorem there, and that is because of the fact that these are at a right angle to each other. So then the next question would be, well, what is the actual angle? And we know that using trig, tangent of theta is 25 over 100. Now, in this case, I would need more context. Is the plane actually going south, or did I just make that up? Because when I find this angle here, I need to think, okay, is that the actual angle for the direction of the plane, or do I need to think about what quadrant this plane should be in, and if this is just a reference angle and things along that line. But again, there would be more context, so I would know how to do that. Okay, so what we're going to look at now is, what if we start with a single vector? How can we find its components? That's going to be the big thing that we're going to get to, because in order to have vectors that are both going in different directions that are not right angles to each other, we need to find the vertical and horizontal components so that we can then add or subtract the vectors to find the resultant. How do we do this, though? Again, it should be pretty straightforward because we understand right triangle trig. So for instance, I know that the cosine of 60 degrees in this case is going to equal the adjacent side, v sub x, over the hypotenuse, v. So another way I can write that is that v sub x is going to be v cosine 60. And that's how I can end up with my 25 meters per second. I also know that the sine of 60 is going to equal opposite over hypotenuse. So that will be v sub y over v, or v sub y equals v sine of 60. And that's how I end up with my 43. So what we did there, and this is what we're going to get to on these next couple examples, is we took a vector and we split it up into its horizontal and vertical components. All right, so I know this isn't Trevi. This is just an actor that I had to hire for this problem. But here we have a dog on a leash, 40-degree angle, and there's a force in the leash, or a tension, if you will, and we are trying to find the horizontal and vertical components of that force. So if I call this V, then I know the magnitude of V is 60, and I'm trying to find the magnitude of the horizontal and the magnitude of the vertical component. So I want you to try this on your own. Pause the video, unpause when you are ready to check. That is an adorable dog, though. Not as cute as Trevi, but still a nice dog. Looks very well behaved. Yeah, Trevi wouldn't stand there like that. All right, so we end up with the vertical component is 38.567 newtons and the horizontal component is 45.963 newtons. How do we come up with that? Simple right triangle trig. V sub y is 60 sine of 40, so V sub y is 38.567 newtons. V sub x is 60 cosine 40, so V sub x is 45.963 newtons. Again, it's a nice looking dog. All right, next one. Find the angle between the forces given the magnitude of their resultant. So we know the magnitude of each force, force 1 and force 2, and we know the magnitude of the resultant. I'm going to have you try this one on your own. This one's going to be a little bit more difficult than the last one. I'm going to give you a big hint though. So notice that we are not given any direction for any of the forces. So keep in mind that in order for this to be force 1, this to be force 2, and this to be the resultant, there has to be a very specific angle between force 1 and force 2. However, that doesn't mean that force 1 and force 2 have to be at a specific location themselves. So what I mean by that is, just for example, I could have force 1 like this and force 2 like this, and then their resultant would be something like this. All right, and remember that comes from the fact that if we do, if we do vector addition, which is what we're doing here, we would just take force 1 and translate it to force 2. So that's how the addition works. Anyway, but the point being that to make the problem easier for myself, I'm going to intentionally choose force 1 to be on the positive side of the x-axis. So that would be my recommendation. The reason why we can do that is because, again, this orientation right here, if I just take that, I can rotate it however I want, and I can put these vectors wherever I want, as long as the relationship between the two forces stays the same. So I want you to go ahead and try and do this on your own. Again, my recommendation is that you're going to put force 1 on the positive side of the x-axis, and you can do that because that's your choice. So pause the video, try this, unpause when you're ready to check, or if you get stuck. All right, so I ended up with the angle between the forces is 47.384 degrees. How did I come up with that? So here's what I was talking about. So again, I'm choosing, because I don't know where force 1 is located, I just know that force 1 and force 2 have a fixed relationship to each other. They don't have a fixed relationship in space. So I'm choosing force 1 to be on the positive side of the x-axis. So I'm just going to call it vector x. So force 1 in rectangular form then is going to be 3000I plus 0j because I'm choosing it to be on the positive side of the x-axis. That's the part that makes the problem easier. I'm going to call force 2 vector y. So vector y is 1000 cosine theta I plus 1000 sine theta j in rectangular form. I don't know what theta is, that's what I'm trying to find in the problem. So theta here in my picture is the angle between x and y. The resultant, which is the sum of the two forces, is x plus y. I don't know that angle either. Do I know that this is the exact orientation of the vectors? Not exactly, but since this is larger than either of these individually, I know that they are going in relatively the same direction, because if I add two vectors and then I get a smaller force, a smaller resultant than one of the two vectors, then maybe y was going off in this way or down this way, or, well, not over there. But they have to be going relatively in the same direction. And again, if I was to just show the actual addition, this is also vector y, right? Okay, so now I'm just going to come up with an equation. So I know x plus y is the resultant. So that's 3000 plus 1000 cosine theta I plus 1000 sine theta j. But I don't know anything about x plus y, but I know the magnitude. So the magnitude of x plus y is the square root of 3000 plus 1000 cosine theta squared plus 1000 sine theta squared, and this has to equal 3750. Now, although the numbers get really large, this is a simple algebraic equation to solve. Square both sides, multiply out these quantities squareds. Notice here, this is something we have to identify. I've got 1 million cosine squared plus 1 million sine squared. So I can factor out a 1 million from both of those, and I'm left with 1 million times the quantity cosine squared theta plus sine squared theta, but that just becomes 1. So that's how I end up with the 9 million plus 6 million cosine theta plus 1 million equals 14,062,500. Solve for cosine theta. Cosine theta equals this over this. Divide those, cosine inverse, and I get 47.384. Answer in the context of the problem. Last one. Forces with magnitudes of 125 newtons and 300 newtons act on a hook. The angle between the two forces is 45 degrees. Find the direction and magnitude of the resultant of these forces. So I want you to try this on your own. This one's going to be a little bit easier than the last one, but similar still. Similar idea, we just know more information. Pause the video, try this, unpause when you're ready to check. All right, so here we should end with the direction of the resultant force is 12.821 degrees, and the magnitude is 398.319 newtons. How do we come up with that? Okay, well, I called this vector x. It has a magnitude of 300, and I know that it's at an angle of 0. So it's 300 cosine 0I plus 300 sine 0j in rectangular form. The sine of 0 is 0, the cosine of 0 is 1, so this becomes x is just 300I. I called this vector y. I know that's at a 45-degree angle with a magnitude of 125. So in rectangular form, it's 125 cosine 45I plus 125 sine 45j. Cosine of 45 is root 2 over 2. Sine of 45 is root 2 over 2. So I can simplify that. The resultant vector, I'm calling x plus y. So it's 300 plus 125 root 2 over 2I plus 125 root 2 over 2j. Find the magnitude of the resultant, square root of the components squared, and I get 398.319 newtons. Find the direction, so tan theta is b over a. So 125 root 2 over 300 plus 125 root 2 over 2, tan inverse, and I get 12.821 degrees. Make sure that my angle makes sense, and it does. I know my angle should be less than 45 degrees, because if these two are 45 degrees apart, the resultant has to be somewhere in the middle, and it's going to be, also keep in mind, so since this, the x vector, was the larger one, the resultant should be closer to that vector. All right, remember how to find the direction, understand how to use the trig form of vectors in order to deal with applications.